In September 1949, an American weather monitoring plane collected air samples over Japan and found traces of radioactive material. The short half-lives of the isotopes pointed to only one possible origin. The Soviet Union had successfully built and detonated a nuclear bomb. The American monopoly on atomic power was abruptly over. Viewing the situation through the lens of pure logic, some military leaders concluded the safest option was to launch an unprovoked nuclear strike while the U.S. still held an advantage. Game theory founder John von Neumann summed up this aggressive mathematics. If you say why not bomb them tomorrow, I say why not bomb them today. To navigate this terrifying new reality, the military turned to the RAND Corporation. This U.S.-based think tank was tasked with finding a structural, mathematical solution to the escalating standoff. When human survival is reduced to strategic logic, finding a structural alternative to mutual destruction is the only way to avoid a terminal outcome. Inside RAND, two mathematicians had invented a theoretical game that closely mirrored the US-Soviet conflict. Today, it's known as the prisoner's dilemma. This grid shows how the game works. A banker offers you and an opponent a choice: cooperate or defect. If you both cooperate, you each get 3 full coins. If one of you cooperates and the other defects, the defector takes 5 coins and the cooperator gets nothing. If you both defect, you each get a single coin. Let's map out your options. If your opponent cooperates, you could cooperate and take 3 coins, or you could defect and take 5. In this scenario, you get the highest reward by defecting. But what if your opponent defects? You could cooperate and get 0 coins, or you could defect and at least walk away with 1. Defecting remains your safest play. Because defecting is the strictly rational choice, regardless of the other player's move, both rational players will betray each other. You both walk away with a single coin, completely missing out on the mutual 3-coin reward. This specific mathematical trap scaled up to the global stage. It led the US and the Soviet Union into a $10 trillion arms race, building tens of thousands of weapons neither could safely use, leaving everyone worse off. The original Matrix assumes a single, isolated interaction. Real life rarely works that way. If you know you have to face your opponent again tomorrow, the underlying math of the dilemma changes. In 1980, political scientist Robert Axelrod set out to test this repeated game. He invited game theorists from around the world to submit computer programs, each executing its own strategy, to play against one another in a 200-round tournament. Many experts submitted complex algorithms. Some were built to hold lifelong grudges after a single betrayal, while others would sneak in unprovoked defections to exploit their opponent's trust. When the results were tallied, the elaborate, aggressive programs lost. The winner was a surprise, a highly simple 4-line piece of code called tit for tat. It opened the game by cooperating, and then it simply copied whatever the opponent did on the previous turn. Axelrod analyzed the data and found the top-scoring strategies shared 4 strict rules. They were nice, meaning they never defected first. They were forgiving, willing to cooperate again after a retaliation. They were retaliatory, immediately striking back if provoked. And they were clear, operating predictably so others could establish a pattern of trust. Even in an environment designed entirely around self-interest and points, being predictably fair and maintaining strict boundaries outperformed trickery and aggression. To see if these traits held up, Axelrod stress-tested the results in an ecological simulation where strategies that scored high points reproduced, and those that lost went extinct. Tit for tat easily survives early exploitation, multiplies, and eventually absorbs spaces entirely dominated by selfish, aggressive algorithms. But computer simulations are flawless. The real world has noise. What happens when a player tries to cooperate, but due to an error, it looks like a defection? In 1983, a Soviet early warning system detected incoming US missiles. It was a signal error. The radar had confused high-altitude clouds with a nuclear strike. If the officer on duty hadn't recognized the glitch, the retaliatory strike would have been catastrophic. When pure tit-for-tat encounters a mistaken defection like this, it immediately retaliates. The other side copies that retaliation, locking both players into an endless echo chamber of mutual destruction over a single glitch. To survive a noisy environment, the strategy requires an update: generous tit-for-tat. By building in a 10% margin of forgiveness, refusing to retaliate on 1 out of every 10 defections, the algorithm breaks the retaliatory cycle. Here's a paradox buried in the tournament data. Despite winning the overall competition, Tit for Tat never actually beat a single one of its opponents. Because it only ever copies the last move, it is mathematically impossible for Tit for Tat to score higher than the program sitting across the table. It can only draw or lose. We often operate under the assumption that life is a zero-sum game. We act as if there is a finite amount of success, and for us to win, we must take points directly from the person we are playing against. In non-zero-sum environments, you don't take your reward from your rival, you take it from the banker. By coordinating their choices, both players generate a higher cumulative payoff from the world around them. This cooperative model is exactly how the Cold War began to de-escalate in the late 1980s. The US and the Soviet Union didn't abolish their massive arsenals overnight. They destroyed a small fraction of their nuclear stockpiles each year, checked to ensure the other side had matched the effort, and then repeated the process. They established trust through verifiable, reciprocal actions. In the short term, our immediate environment dictates the strategies we use to survive. But over the span of hundreds of interactions, the choices we make actively construct the environment we live in. To thrive over the long run, be nice, forgive quickly, hold clear boundaries, and remember that you do not need to defeat your opponent to succeed.